Thank you for coming to this ABB Energy Industries session. We're focusing here on carbon capture and storage, the first 50 hubs. So this is a part of the ABB series of sessions here at Offshore Europe, all focused on making a world of difference for a sustainable energy future. My name is Kevin O'Donovan. I spend my time looking at new technologies in the energy transition, so I'm quite looking forward to this one because I've had a sneak peek before of what these guys are up to. There's a lot of cool technology under the covers. Now, yesterday at the opening keynote, the minister from the UK was talking about the carbon capture and storage potential in the UK of 78 gigatons. So there's a huge interest in carbon capture and storage out there right now. Some people think it's very hard, some people think it's just same old, and there's a lot of unknowns and people wondering for some clarity. So the purpose of this session is to go through some of the bleeding edge thinking that's going on and projects that are going on around making this a reality. I have the pleasure of moderating the session. I'm joined by two colleagues here. So we have, Nigel Greatorex, the Global Industry Business Manager for CCS at ABB Energy Industries. And we have Matt Healy, the CEO of Pace CCS. So to open this, let me ask Nigel, what is ABB up to with Pace CCS? You had a big announcement back around March timeframe, so what are you up to?
Yeah, thanks, Kevin. Well, firstly, ABB is experts in operating these type of facilities from years of experience in working in the oil and gas sector, and Pace are the experts in designing these facilities. And I think it's important to note that we're entering into a new industry here. So there's significant lack of operational experience. So it's really important that you get this synergy from design through to operations. So working with the experts who design these systems, through to the delivery company who operates these systems, we get that consistent approach throughout.
Matt?
Yeah, it's great to be working with ABB. So Pace CCS, we're a engineering design consultancy. As it says in our name, we specialise in CCS. We are the global leaders. We've got our office in London, we've got one in Houston, and one in Kuala Lumpur. We've been brought on to design on more than 80 CCS projects around the world. Now, these projects are largely in the very early stages. Even the most advanced CCS projects here in the UK are still a few years away from start-up and operations. We are involved with the design, but of course when you're designing any industrial network, it needs to be designed with operations in mind. And this is where ABB comes in, is that we can offer that design expertise. We've got lots and lots of experience, but of course we've got an eye on the important thing, which is successful operation of CCS projects and a successful CCS industry.
Now, I think, Nigel, the key thing you mentioned there is that it's designed through to operations, and we're going to dive into that in a second. But I suppose, back to the theme here. When we talk about hydrogen hubs, what are we talking about? Or, sorry, carbon capture hubs, what are we talking about?
Well, the definition of a hub really is a CCS network that's taking multiple third parties CO2, either compressing it or transporting it in gas phase via pipeline or via ships, and then disposing of it in a subsurface reservoir. So with that comes huge business risks, because a lot of these networks operate on a take or pay scheme, meaning the operator of the network, if that network isn't available, either for the above surface operations or the subsurface element, then they're going to run into huge financial damages as a result of their client, the emitter, having to vent the CO2 to atmosphere. So availability is the most important element of how you design these networks and how you operate them, because availability is a direct correlation to mitigating business risk.
And if I may, so instead of, oh, I've got a great design, then I build it and I figure out it doesn't work according to what I expected, then I have a risk. Now, Matt, you had said this has not been done before. And anything that we haven't done before, people will be skeptical. Well, how do we know how to do it properly? How do we de-risk something we haven't done before?
Yeah, I think the first thing that you can do is draw on the experience that we have with carbon dioxide. It is a very common industrial chemical, and there are CO2 EOR projects, enhanced oil recovery, as well as a few smallish scale CCS projects that have been in operation for some time. The biggest risk, I think, from a fundamental perspective, is the integrity of the system. If we have an industrial hub, which means there's shared infrastructure, which means that we've got multiple emitters, as Nigel was just saying, going into common pipelines and common shipping, the risk is to that infrastructure, because if you lose the infrastructure, then you lose the entire network. Corrosion is probably the biggest of the integrity risks. There is potential for corrosion in CCS projects. We all know if we get water in CO2, that can be very corrosive. But when you mix CO2 from different industrial emitters, it comes with different impurities. Those impurities can react together, and they can create very corrosive substances like sulfuric acid. And then finally, we've got other substances like glycol, like methanol, that are very common in these networks. And they can interact with water and also create a corrosive substance. So from a fundamental risk point of view, integrity is key.
Now, if I may, but how do I convince someone that I'm taking the risk out? Is it simulation? Is it taking that expertise? How do I build on that?
Yeah, it's good design. As engineers, this is what we do. We design systems, we take advantage of the experience that we have, of research, and we bring these together to try and create something with that focus on operations which is robust, something which is absolutely bulletproof. There is plenty of research going on. We're just across from the Net Zero Technology Centre that we're working with to help develop and improve our corrosion models. But fundamentally, it's about making sure that you understand the system so that you can operate always outside of those areas. Now, you can only do that if you understand exactly where you're operating.
Yeah, and I think just to add to that, there's one thing designing these networks, and as Matt says, it's then how you operate them. And because the nature of these complex hub networks, you'll have various operating conditions that a normal control system cannot react to those changes. So you're needing to build like an advanced process control system that sits above the control layer in order to be able to adopt to operational changes. Now that could be an emitter going offline. An emitter going offline does not give the network operator any warning. And a huge transient like that can cause operational upsets, but yet at the same time, your injection ratios that you're sequestering the CO2 need to be steady state because of the equation of state of CO2. So it's important that, and all of that comes back to availability again. If you get certain emitters that turn down, if you get certain emitters doing a kiln changeover in a cement application, all of this is going to destabilize the network that you're trying to stabilize in terms of its operability as best you can, because an unoperable network means significant financial risks. So what ABB is doing, along with Pace, is we are designing a digital solution called the ABB Balance of Operations. This is made up of two digital twins, in essence, an above surface digital twin and a subsurface digital twin. And then those two twins come together to provide a holistic digital solution across the whole network, whereby taking those simulated values from the twins, we can provide operator guidance that when you have got those operational upsets, you can get that operability as best you can throughout the network.
And if I may, you said the magic word digital twin, because I'm a big fan of the technologies. But let me play devil's advocate for a second. The oil and gas industry. They've been building complex things for generations. And I often hear, look Kev, we know how to do this stuff. We've designed the stuff, we operate the stuff. This is just the same. You're saying this is different, right?
Well, it's different in many ways. First and foremost, when you look at oil and gas applications and transporting hydrocarbons, that doesn't come with anything like the business risk that an operator of a network, CCS network, comes. So, if you have a production well shut down, you produce less oil and gas, but there's no third-party liabilities associated with that. So it's all around mitigating business risk by ensuring high availability and deploying emerging technology to give operators the confidence they can meet the obligations of their customers by consistently taking third-party CO2.
Now folks, if you have any questions, please do raise your hand. We will be audience participation. We have a couple of roving mics, so think about your questions. But if I may, Matt, we still kind of come back into the industry and they kind of go, yeah, but it is new. And we've had some experience with enhanced oil recovery, and people are dabbling with it and whatever. And you've got the digital twin technology and simulations or whatever. But how do you then work with a customer to say, look, we can still de-risk it by the way you use the technology, the digital twin, the physics models, the expertise from the experts, and create that real-time digital twin, if you like?
Yeah, in oil and gas and in EOR, we've got the luxury of having operations teams with decades of experience. There's, teams that have seen it all before. They know how to start up oil and gas wells. They know how to operate pipelines from one place to another. We're not going to have that. We're dealing with lots and lots of challenges related to design because it's new, and that requires a more creative approach to some of these problems. An example is we need to model the full chain, which is something which is not really required with oil and gas. And so that's why we've developed our digital twin, now ABB's digital twin, as part of our partnership, to understand the full chain and be able to model that. So there is plenty of things that we can learn from good practices in the oil and gas industry, from operational experience with EOR projects and with CO2. But because it's a new industry and we don't have the experienced operators, we need to design and give them as much help as possible to make sure that these systems, that we protect their integrity, and as Nigel's pointed out, we have high availability. These things stay online because it's how they make money.
Well, it's the business model, you said. Nigel?
Yeah, I mean, just to add to that, I think most people in this room have got some past experience in oil and gas, and most people who have been involved in designing oil and gas projects will have come across certain tools that are being designed for oil and gas applications. The majority, if not all of those tools, are not transferable into the design of CCS networks. So to think we've got all this year's experience in all these tools, this is a completely new industry, and the complexity of modelling the transportation of oil and gas compared to CO2 is completely a different end. So we need new tools, we need new skill sets, we need lots more experience that we haven't got, and that's what ABB and Pace can help bring to the table for you.
Now let me come back to the technology angle. We talk about digital twins, and digital twins mean many things to different people, and I'm guessing many people in the audience say, yeah, we've had digital twins for years. Now the key of your partnership, you've got the subsurface digital twin, you've got what Pace are bringing to the table. Could you give some idea of the capabilities that both twins bring to the table? So from the undersea side, the subsurface side.
Yeah, and I mean the difference is you can use these twins in isolation for design purposes, but you need these twins to come together into that holistic solution for operational purposes. So even bespoke twins that are being developed and designed for CO2 applications, they need to come with this holistic approach, because when you're looking at operational risk, you're looking at everything from the point of CO2 coming into your network all the way through to this disposal reservoir. And you need to be able to model that to actually manage the operational changes and transients in order to give you that availability. And with one twin operating in isolation of one another, it's not going to give you that holistic view and guide operators when you've got a process upset at either end of your network.
Matt?
Yeah, so from a technology perspective, it means that we've got a thermodynamic model, so we understand the fluid, we've got the pipeline and process models, we've got the ability to predict chemical reactions, we've got the ability to predict other factors that can cause corrosion, and all of those things that we are concerned about from an operational perspective, and it's all there to provide support to the operations team to make sure that we maintain that availability and the integrity of the system.
So folks, any questions? No question. Everyone told me that everybody in Aberdeen was always very chatty. And you're all very quiet. Now, Matt, we had the opportunity, I met you through ABB at CERAWeek. We have all of the investment through the Inflation Reduction Act, we've got Repower EU, we've got the investments here in the UK, and pick a country, they're all competing for the same, if you say, to get ahead. What's the appetite out there for CCS projects today?
It's really high. It's driven by the need to combat climate change, and that means going net zero. Now, most countries have got either a target, or in some cases like the UK, a legally binding target, so in law to reach net zero, in the UK's case by 2050. Fundamentally, that's what's driving it. We've been producing CO2 for an awfully long time. We're currently putting more CO2 into the atmosphere. faster than we have ever done so before. CCS is about waste disposal, and so that means that there's a global need to stop putting CO2 into the atmosphere, and then it's just a question about the regulations that you have to reach that goal. In the US, they have the IRA, the 45Q tax breaks, which encourage investment from private industry because it becomes a profit-making exercise. In Europe, it's more about having a bit more, less of the carrot and more of a stick, and ratcheting down CO2 emissions over time to give industry time to adapt. And then in Asia, it's different again. There are different drivers. So, but fundamentally, it's driven by the need to stop putting CO2 into the atmosphere as quickly as possible. CCS is part of that solution. It's not the entire solution, but it's a key plank in that particular requirement.
And Nigel, from the ABB perspective, your core customers, new customers?
Yeah, I mean, it varies. If you take the North Sea, which I guess most people are familiar with, sat in here in Aberdeen, pretty mature basin, lots of production assets coming to the end of their life, lots of pore space, subsurface, and of course no operator wants to go through the cost of decommissioning these assets to get a certificate to say you've met the regulations. So if you can repurpose those assets and give another 25 years business life, then happy days. But you know, the key word in that is business. The Paris Accord that's driving this was signed back in December 2015. And yet in 2022, we still, from hydrocarbon sources, put more than 1 billion tons of CO2 to the atmosphere over and above 22 levels. So we're still going in the wrong direction, and that's being driven by government policy and the policy changes. So there's incentives in the US. We're seeing venture capitalists and hedge funds all trying to get their hands on the tax dollars on the one hand, and certainly in Europe we're seeing a lot of the IOCs who have got those assets coming to the end of their life looking to repurpose. But one thing's for sure, people are going to do this to either mitigate their financial exposure or to make money. And it's really driven by government creating that fiscal environment as such that people can actually make money. And that's probably why we've gone 8 years without really improving our net emissions content that's going from fossil fuels into atmosphere.
Well, we were just chatting prior to this. There's been a raft of announcements from some of the big players in the last 3 or 4 months investing in carbon capture, buying companies. You know, this isn't kind of a fad that's going to go away, right? It's here for the time. Any questions, folks? Question here in the front. Have we got a row? There we have. Thank you, Jess.
Hello, my name is Sheena Martin. I work for Tenaris and we are manufacturers of steel pipes. So, related to line pipe and the topic of repurposing, what would be the process to check the condition of the existing pipelines in order for them to be used to transport the CO2?
Yeah, it's a really good question, and this is a challenge. There are real opportunities to repurpose line pipe because CO2, when properly treated, can be entirely benign or only very mildly corrosive, depending on the cocktail of impurities that are in place. And that opens up the ability to reuse oil and gas pipelines, for example, that have been in operation for many decades. The challenge is it's very difficult to test the condition of a pipeline which is buried. And so the answer is you do what you can. So you go through a requalification process which is very similar to the qualification process that you would go through to extend the operating life of a pipeline. And then it's a matter of understanding how the impurities that come with the CO2 can impact the integrity of the pipe. I mentioned right at the beginning that you absolutely will need to avoid having chemical reactions that can form strong acids. You will need to dehydrate your CO2 to prevent water from condensing. And then you need to look at other factors as well that can be mildly corrosive. There are plenty of examples of projects around the world and in the UK. HyNet is a project that we at Pace are very familiar with, and they are reusing a lot of the oil and gas pipelines and indeed offshore infrastructure as well. So there is an opportunity there, but it needs to be done carefully and in harmony with the design of the industrial hub.
And if I may, I suppose, because it's not just, if I may, just a spreadsheet and I'm ticking off boxes, because you've got the physics models, you've got proven chemical reactions, the data that comes from the pipe survey, if I want a better word, you feed all that in, and then you might find maybe there's a piece of a pipe that needs to be fixed or whatever, right? So
Because there isn't that much operational experience, it seems weird to say, but the CO2 with small amounts of impurities in it was not a fluid of not much interest until quite recently. And what that means is that we are still learning things, particularly around integrity and corrosion. There is plenty of laboratory work going on. We're doing some of it ourselves, and there's lots of it being done in the US and Europe to understand these issues. But fundamentally, the risk is being brought what comes along with the CO2.
Okay.
If you had pure CO2, it's benign, entirely non-corrosive to essentially any metal pipeline. But then we have projects in the UK and in Europe that, for example, have banned glycol for dehydration because of the corrosion risk introduced by glycol. And HyNet is one of those projects. Aramis they've published their specification, and they've also taken the same step. And I'm aware of other projects that have done that. So when you're repurposing pipelines, or indeed designing a new pipeline, you need to understand what the risks are that are being brought on by the fluid. And as Nigel pointed out, also right at the beginning, the fluids are coming from different sources. If we have an industrial hub, then we have different impurities that come from those different sources. And a steel refinery will be different from a power plant, will be different from a blue hydrogen plant.
But the ability to be able to take all that data, put it into the digital twin and simulate all the different possibilities.
Absolutely.
We didn't have that before.
That's right, yeah. So this is new, and this is something that we're able to bring to the table, is that the compositional measurement gets done at the point that at each emitter where the fluid is going into the pipeline, and then we can calculate the corrosion risk, or if there is a corrosion risk due to chemical reactions, due to aqueous liquids, or due to some other source of corrosion or risk to integrity.
And I think when Matt talks about corrosion risk and we're able to model that from a design perspective, again, it comes back to my earlier comments around the importance of design is one issue, operations another. So whilst those third-party emitters will be under contract to provide CO2 within specification of their contract, if there's a process upset and they go off spec, how do you alert the operators that you may have to shut the block valve and take them offline before they cause significant integrity breaches of your infrastructure? Well, again, the balance of operations that ABB and Pace are developing, we have full composition tracking built into that model, so we can protect the operators from that risk to a large extent.
Sir, there's a question here.
Thank you. This is a follow-up to the conversation about pipelines. None of the pipelines you're talking about as far as decommissioned offshore pipelines are clean steel pipelines. They're all scaled. They've got various compounds in them. What are the issues with that relative to the pipelines? And should we be looking at going forward with decommissioning that we have some standards enforceable to leaving pipelines in place that have potential for carbon transport that have had some sort of flushing activity that would make them suitable? Because right now the standards are just getting to a low hydrocarbon level, not even that low. And we're looking at 30 parts per million on the discharge from these pipelines, which does not take into account anything with what's on the inside of the pipeline, just on the hydrocarbons that are being emitted.
Yeah, it's an excellent question. It's a difficult one to answer. As you say, that there aren't standards for this, except to say that it needs to be done with good engineering and due diligence. There are certainly pipelines that are not suitable for CO2. One particular example is pipelines that have an internal coating, because CO2 can dissolve the internal coating, which can cause issues. When it comes to the byproducts that you have on the inside of a pipeline due to corrosion over decades of experience, that is something that needs to be thought about. The key issues is, of course, making sure the pipeline is dry, because once you introduce the CO2, that will acidify any residual water, and indeed it will acidify any residual glycols or TEG, which is often used for drying the pipelines, and so that introduces a risk. When it comes to the other residual elements that can be there, I think it's sensible to consider what impact they can have, but ultimately they will be consumed if they are involved in any sort of corrosion or other chemical reaction, which means that it's limited. It's not a continuous corrosion, it's a one-off. So I think that absolutely needs to be thought about when it comes to understanding the operating pressures and ensuring that you have enough wall thickness in your pipeline to operate with CO2. But based on looking around at the projects that we worked on, that repurposing process has been achieved on several CCS projects, and several more are going ahead with intending to reuse pipelines, either midstream or upstream oil and gas.
Folks, I'm afraid the clock is against us. The contact details for both Nigel and Matt are here. Obviously, they'll be around afterwards, but you can reach out to them. They're both on LinkedIn as well. Before we close, Matt, if there was one takeaway statement you wanted the people to leave with, what would it be from your side?
I think it's designing with operations in mind. We have seen many CCS projects.
That was my takeaway.
I think it's the takeaway. We've seen CCS projects, and Gorgon is a high-profile example where things have gone wrong. And those things have gone wrong largely because we're going into design with an oil and gas mindset or with an EOR mindset. This is a new industry. It does require creative engineering. Engineers, in my experience, are generally very good at this, and they relish a new challenge. And so I would be wary of making assumptions that might make sense in one industry but don't necessarily make sense for CCS.
Yeah, I mean, I can only echo what Matt said. 20 to 30 years experience in oil and gas doesn't qualify you to work on a CCS project. It contributes, and it's a big contributing factor, but this is a new industry we're entering. So considering operations in your design phase and how you're going to run those to de-risk is absolutely essential.
Folks, whatever you take away, CCS is not going away. It's not a fad. It is different, but the people that are out there, I spend my time in the digital world, digital trends, industrial metaverse, whatever. What these guys are up to is different. There's not many people in your industry doing anything like this, so do take a look. It's interesting times. Thank you very much, gentlemen.
Thanks,
Thank you.
Thank you.